The next variable that affects stroke volume and therefore cardiac output is something called contractility. In the molecular perspective, this really involves more myosin cross bridges being formed, more calcium being released into the intercellular fluid, and so more force being generated. The contractility is predominantly regulated by the sympathetic nervous system. If we take a look at this graph over here, this is a variation on the Frank-Starling law of the heart graph that we just saw. You can see that we have end diastolic volume and preload graphed on the x-axis. On the previous graph, I showed you stroke volume being graphed. Here it graphs cardiac output, but you'll remember that stroke volume and cardiac output are proportional to one another. So if we look at normal contractions, so this might be, for example, the amount of force being generated in response to ventricle filling and sarcomer length and venous return and so forth, that this is my normal contraction at rest. Okay. If I go to bed, or in this example, heart failure, but even just going to sleep, let's draw a going to sleep graph. You know, I'm just going to go to sleep here, okay? So I'm going to see decreased contractility. It doesn't have to be extreme like you're dying, heart failure, but just, you know, sleeping. I'm going to go to bed. I don't need as much heart output, cardiac output. Okay, so we have our decreased contractility. That is really, it's tempting to say, oh, that's parasympathetic, but actually what it is less sympathetic. So less sympathetic equals decreased contractility. And then you have normal contractility. And then if you want increased contractility, let me color green on top of green here, but this top line here, this is what we would see, say, during exercise or times of stress. As we need to increase cardiac output because we quite simply need more blood. So how does that work? That's going to be increased. So more cardiac output due to more sympathetic activity. Come on, pen, work with me here. Sorry about that. There we go. More activity equals increased. And in a nutshell, what it's doing is it's increasing the amount of calcium available for contraction, which means we have more myosin cross bridges forming. Agents that increase contractility, that make it happen, that generate more force, are called positive ionotropic agents. Okay, positive ionotropic agents. The endogenous ionotropic agents are the neurotransmitters released from the sympathetic nervous system that bind to the beta adrenergic receptor. Epinephrine also, the hormone epinephrine, binds to the beta 1 adrenergic receptor. So if we get norepinephrine or epinephrine binding that beta 1 receptor, we're going to get increased contractility. We'll also, by the way, get increased heart rate, but we're not talking about that right now. We're just talking about the force generated. And we call that ionotropic agents, positive ionotropic agents, generating more force of contraction, more oomph, if you will. And then we have negative ionotropic agents that decrease the force of contraction. And again, in this case, it is not, okay? I want to make sure you understand this. Don't make this mistake. It is not the parasympathetic nervous system. Parasympathetic regulates heart rate, but not contractility. Repeat that. Parasympathetic nervous system regulates heart rate, but it does not affect contractility. So it is not going, acetylcholine in this case is not a negative ionotropic agent. Watch for that. I might ask a true-false question about it. True or false? Acetylcholine is an ionotropic agent. The answer is false, okay? Make sure you get that. There are, of course, exogenous, not endogenous, ionotropic agents that will increase heart rate. We actually have quite a number of them. I'm sorry, correction, will increase the force of contraction. We have a number of them that can be used and are used, in fact, to treat congestive heart failure.